These smart streetlights, accompanied by cameras with image processing capability, will use RCNNs to sense objects in the surrounding. This will be used to automatically control whether that streetlight is on or off, and if on, to what value of intensity will it be set, according to the number of vehicles detected and their distance from the streetlight. Each streetlight will have an LDR to calculate the amount of sunlight present and thus the intensity of light to be emitted. The brain of this project is a Raspberry Pi. Each streetlight will be powered by a heliostat solar panel, essentially sun-tracked panels moving in the direction of maximum sunlight. This process will be connected to a cloud-based mobile app to display all the real-time information and also to detect any problems. This app will detect the exact component in which the problem lies and display the same for the relevant authorities, who can then send technicians to repair the streetlight immediately. By my calculations, this system will utilize zero electricity and only resort to the 12-volt battery power at night. Solar panels will cover all the street electricity needs for the foreseeable future. The main statistic I am looking at is the initial cost required for implementation. This will be completely paid for by the self-sustaining heliostat solar panels in an astonishing 5 to 6 years. This is the automated smart street lighting model using integrated systems with deep learning and cloud deployment. As aforementioned, it can be divided into three parts: the continuous electricity provision using self-orienting solar panels, the deep learning model to detect vehicles on the road, and the cloud-based app for data collection, data tracking, and quick repair functionalities. As you can see, this prototype consists of two streetlights. However, this can be scaled up quite easily, following the same pattern to suit any road. This system's primary target is residential areas, where 100% brightness of streetlights is not required the entire time. Let's start with the first system, the continuous electricity provision using self-orienting solar panels. This has been constructed using an Arduino Nano, two servo motors, 3 LDRs, and a solar panel. As you can see in this demonstration, it follows the direction of maximum sunlight in order to provide maximum electricity to the system. I'm also delighted to say that the entire system is powered by these solar panels. The solar panels provide electricity to the 12-volt battery, which in turn powers the system. At night, the 12-volt battery keeps powering the system from the remainder of the electricity it had received from the solar panels during the day. In this sense, the 12-volt battery is essentially a container for electricity obtained through the solar panels, not generating any external electricity itself. This is what makes the system extremely efficient. My original plan was to have 4 LDRs in the 4 cardinal directions of the solar panel: north, south, east, and west. However, after designing the model, I had a realization that the difference of brightness, which is the main concept on which the self-orienting solar panels work, is not much, leading to very little movement in the direction of the solar panels. As a result, I moved to this new system in which 3 LDRs will be used with barriers in between. Therefore, the difference of sunlight on each of the LDRs will be vast, since a shadow will be created on the LDRs which are not on the side of sunlight. This makes the system almost twice as efficient. These solar panels will be located on each streetlight and will result in complete electricity generation for the system. The next system is a deep learning model to detect vehicles on the road. For this, I've used a camera to record the entire length of the road. As the instantaneous input picture is received from the camera, the image is run through a region-based convolutional neural network, which is a subpart of machine learning algorithms. This model creates boxes around vehicles and humans detected in the image. If a vehicle or human is detected in the image, a signal is sent to the Raspberry Pi. The model is almost 93% accurate and has been trained and tested with over 2,000 images. Based on the number of vehicles as well as the distance from the vehicles to each streetlight, the intensity of the streetlights is set. More the number of cars or closer the cars to the streetlight, the brighter the light. These NeoPixel LEDs are used to replicate the streetlights in our prototype. They have 5 levels of varying brightness depending on the 2 factors mentioned. In this way, we have achieved high efficiency. As you can see, the closer I bring this car to the streetlight, the brighter it turns. Now, if I replace one car with 2 cars, the LEDs automatically turn brighter, since two cars require more light than one car. However, this is not the only factor that affects the brightness of the street light. I've also taken the average value of the three LDRs on each solar panel into consideration. This way, we can detect the brightness of the surrounding and automatically supply only that much brightness as is required. Both of these processes work in synchronization effectively to save a lot of electricity. The next system is a cloud based app for data collection, data tracking, and quick repair functionalities. This is the app through which all data will be monitored. Through the Bluetooth module on the Arduino Nano, we can transfer data to the app. Once the street lights are connected, we can see all the data, including the average brightness value, electricity provided by the solar panels, electricity utilized by the street light, and working status, whether yes or no. These streetlights are categorized on the basis of street and further on the basis of city for quick reference. If a streetlight is malfunctioning, a red sign is flashed across the app page for that particular streetlight. The component that is malfunctioning is displayed as well. In addition, a notification with the location of the malfunctioning streetlight and the faulty component is sent to the cloud based app. The relevant authorities in charge of the app can then send technicians for swift repairs. The goals of this prototype include saving immense amounts of electricity, saving immense amounts of government spending in the long run, ensuring quick repair functionalities of malfunctioning streetlights. It also furthers three United Nations Sustainable Development Goals: affordable and clean energy, industry, innovation and infrastructure, and sustainable cities and communities. The current streetlights are uneconomically used from 7 pm in the evening to 6 am the next morning, each and every day. This makes them extremely maintenance heavy for the government. In fact, the BMC spends upwards of Rs 150 crore annually on streetlights. The cost could be minimized by using the automated smart street lighting system, which requires zero electricity cost after installation. Furthermore, the streetlights do not have varying levels of light intensity, rather only a binary on-off setting. This wastes a lot of electricity at times when there is adequate sunlight. The automated smart street lighting system eliminates this problem by using LDRs and RCNNs to produce maximum efficiency. According to the LDR values, as well as the number of vehicles detected and the distance of the vehicles from the street light through RCNNs, the intensity of light emitted is determined. Thus, by this method, we can conserve vital electricity in the best possible way. In addition, the replacement of a faulty street light does not take place unless of a citizen's complaint or a physical check done by the contractor. The tediousness of this process is completely eliminated by the cloud-based mobile app, which displays all the real-time information and also detects any problems if present in any of the street lights. This mobile app also displays the location of the faulty street light for the relevant authorities. These authorities can then send technicians to repair the faulty street light immediately. Thank you.